Hi, it's Miss Cook again, and as promised today we're going to look at group 7. I know some of you are in group 7, so let's have a look. Group 7 are also known as the halogens, and people quite often forget this. So the way I remember it's a little bit of a tenuous link, but 7 rhymes with heaven. In heaven there are angels, and above their heads angels have halos, so halogen, halogen, it kind of works. So group 7 elements, as you can see, are here, and as we go down the group, if you remember group 1, as we went down the group, reactivity increases, but this time the reactivity decreases as we go down the group. And again, we need to be able to explain why fluorine is more reactive than chlorine, for example. So yet again, I'm going to draw those diagrams because they really help me visualize what's happening. So here are my diagrams. So I've got fluorine, I've got chlorine. Fluorine's got 2 shells. I've not drawn the electrons on the inside shell just to make this easier. And 7 electrons in the outer shell. Remember, that's why it's in group 7. Chlorine has got 3 shells, and again, 7 electrons in the outer shell. Now, when group 7 elements react, what is happening is they want another electron to fill this spot to give them a full shell. Same with chlorine. Now, fluorine is more reactive than chlorine because it is easier for fluorine to gain an extra electron because it's close to the nucleus. So there's a stronger pull of attraction and there's less shielding from the other shells. For chlorine, it's much more difficult because it's further away. And as you imagine, as you go down the group, it's going to be harder and harder for the atoms to gain an extra electron to become an ion, but to become stable. And that's what we need. We want atoms need to be stable. So they're trying to gain or lose electrons to get there. So fluorine is more reactive because the outer shell is close to the nucleus and therefore it is easier for it to attract another electron. Now, our group 7 elements are all actually diatomic, so that means they go around in 2s. So if we were to write an equation, we wouldn't just write F, we would write F2, unless it's bonded to something. So just to explain why, so that you can remember this, obviously this is our fluorine again, just as a reminder. When they join, they're going to join up like this. And this is a covalent bond, so they're going to share the electrons. So fluorine has 7 electrons in its outer shell. It needs 1 more to have a full shell. What's going to happen is the fluorine atom is going to put its electron in the overlap, and we'll have the 6 others around the shell. Now, this second fluorine is also going to put an electron in the overlap. I'm going to draw it as a dot this time so you can see the difference. And its 6 electrons are around the outside. And now each fluorine atom, has a full outer shell, and therefore is stable. And this is why they go around in 2s. So we would always write fluorine as F2 if it's not bonded with something. Now, if we look at the melting points of elements in group 7, what happens as you go down the group from fluorine along to astatine, the melting point actually increases. And you might already know fluorine and chlorine, bromine are gases at room temperature. Iodine and astatine are actually solids. So that's an easy way of remembering it. If it's a solid, it must have a higher melting point. Now, why is this the case? So our fluorine atoms obviously form our molecules, and holding the molecules together are things called intermolecular forces. Now, these are quite weak and they're fairly easy to overcome. As our molecule gets bigger, so iodine's a much bigger atom, therefore a much bigger molecule, there are more intermolecular forces, so therefore they are stronger and more energy is needed to overcome. So as we go down the group, they get higher melting points because of stronger intermolecular forces, which take more energy to overcome. Last thing on group 7, something that is further up group 7 can displace something that is lower down group 7, obviously because it's more reactive. So if I react chlorine here, Cl2, with potassium bromide, KBr, what's going to happen is the chlorine is more reactive than the bromine, so it's going to displace it, it's going to take the place. And I'm going to do it with potassium chloride and bromine. Now, you might wonder, first of all, where's that 2 gone? Why has it disappeared? Why is there 1 here instead? This equation isn't balanced. I can balance it really quickly for you. Just pop a couple of 2's on there. The other thing you might have noticed, as I said, we've got chlorine, but we've got potassium chloride. So the name changes ever so slightly, just because this is a chlorine molecule. These are chloride ions that have joined potassium ions, and the name just changes ever so slightly. So let's have a look at this one then. We've got fluorine, adding it to potassium chloride. What do you reckon is produced? I'm hoping you've just said it. We have got potassium fluoride and we've got chlorine gas as well. And again, you can balance this just with the number 2 in front of those 2 molecules.